Hi everyone, we're going to look at parametric equations this morning. So here's a little example of what parametric equations are. For every degree over 70 degrees, our store sells X bottles of sunscreen and X squared pints of ice cream. So go ahead and write an equation to represent the amount of ice cream sold. So I got, let's see, ice cream is equal to the number of sunscreens squared. Okay, so when I square the number of sunscreens, that gives me the pints of ice cream. Okay, so really there's something happening here. Does sunscreen really is sunscreen really going to determine the number of ice creams that we sold? No. Okay, so there's a determining variable for sunscreen and ice cream that is actually the temperature. We call this the hidden variable. More specifically, we rely on the equation. So how could we rewrite, we call this the hidden variable, or the third variable. So we can actually write each one of these equations in terms of temperature, which is, it says temperature every degree over 70. So how could I count the number of degrees over 70? That would be whatever temperature I have, say it's 80 degrees, minus that 70 degrees, I would have a X value of 10. Okay, so we can actually split up the two equations. Instead of ice cream being reliant on the number of sunscreens sold, we can split them up to say that the sunscreen is equal to the temperature minus 70 degrees. So an example would be like, let's say the temp is equal to 80 degrees. The sunscreen would equal 80 degrees minus 70 degrees, which gives me the value of 10 sunscreens. Okay. The ice cream, remember, you square the number of sunscreens, so that would be the temp minus 70 degrees squared. So for ice cream, we get 10 squared, which is 100 ice creams. So this is what we call a parametric equation. It's when there are two or more equations reliant on a common variable, which we call the hidden variable. The third variable. It's often theta or time. Okay, so the two examples we'll use are with time and theta. Okay. All right, example 1. So we're going to sketch the graph and then rewrite the parametric equation as a rectangular equation. So remember, parametrics are written in terms of a third variable. Okay, and rectangular equations are written in terms of x and y, like a coordinate plane, x and y. Okay, so rectangular equation. Oh, hey, look, I thought ahead. Okay, so let's go ahead and what is our third variable for a? Well, it's time. Okay, so we're going to graph this, and the way I graph this, I have to have actually 3 columns. So time, how we're moving in the x direction, and how we're moving in the y direction. So I'm going to go ahead and choose some times, -1, 0, 1, 2, 3. Okay, and then for the x, I'm going to go ahead and plug in -1 minus 4, which is -5, 0 minus 4, which is -4, so on and so forth, -3, -2, -1. So in the x direction, I'm moving linearly. Now let's go ahead and graph in the y direction. So this would be -1 over 2, which is -1/2. Okay, and then 0 over 2, which is 0, and then +1/2, 1, and 3/2. Okay, so we go ahead and we graph these ordered pairs, 5, comma, -1/2. Okay, so 1, 2, 3, 5, -1/2. I'm going to zoom. Okay, and then we go to -4, 0, -3, 1/2, -2, 1. This looks like a linear graph. Okay. And then I go ahead and connect an eyeball. Okay. And then we also have to know which is the first dot. So the first dot that we graphed was this one at -5, 1/2. And the last dot we graphed is at -1, 3/2. So I know that the order that parametric graphs are directional. So these points are moving in this direction. Okay. So we do have to add the arrows in there. You don't need that many, but you need arrows. Okay. So that's how we graph a parametric equation. Now let's change the parametric equation to be in terms of x and y. So we're going to go. So our equation is x is equal to t minus 4 and y is equal to t over 2. Okay. What we're going to do is we need to, you know what? We need some directions. Okay, first, we're going to change to rectangular form. Okay, which is in terms of x and y. So the first thing we're going to do is solve one equation for t, and then we're going to substitute. So our goal is to eliminate t. So we're going to substitute t into what the other equation. To the other equation. It doesn't matter which one you start with, just like other systems. Okay. So I'm going to use the x equation. X is equal to t minus 4, and I'm going to solve for t. So x plus 4 is equal to t. And then I substitute this x plus 4 in for t. So y is equal to t over 2. So y is equal to x plus 4 over 2. And now I've eliminated my t variable. I'm going to just rewrite this as 1 goes into both. 1/2 x plus 2. And I'm just going to look to see that this equation right here, let's see, the slope is 1/2 and the y-intercept is 2. Oh, the slope is 1/2 and the y-intercept is 2. I think we graphed right. Okay. All right, let's look at B. Go ahead and graph and also change the equation. Actually, let's change the equation into rectangular form. Okay. So just like we did before, step 1, I'm going to use the top equation. X is equal to t minus 5. So x plus 5 is equal to t. Step 2, y is equal to t squared. So I go ahead and just sub in this. Y is equal to x plus 5 squared. This seems a lot easier for me to graph. So the vertex, this is my h, my k is 0. So h is -5 and k is 0. So I'm going to go ahead and graph 1, 2, 4, 5. And my stretch value is 1, so I know I move over 1, up 1, over 2, up 1, 2, 3, 4, over 3, up 1, 2, 3, 4, 5, 6, 7, 8. Nope. 9. There we go. Symmetry. Okay, so remember we have to figure out which direction these points are moving. So the way I do that is I just think a little logically about this for a sec. So I'm going to take x is equal to t minus 5. And I'm going to go ahead and start subbing in t values. So t is equal to 0. So I get x is equal to -5. I'm going to do t is equal to 1. Actually, let's write this different. We're going to call this x of t, because t is the input, equals t minus 5. So x of 0 would be -5. X of 1 would be -4. X of 2 would be -3. So as time goes on, I'm starting at x equals -5, then -4, then -3, then -2. So the points are moving in this direction. Okay, so again, we need those little arrows. All right, let's stop there and we're going to go to another video.